Before I introduce our distinguished speaker, I would like to say a few words about the organization of this symposium. As is well known, of course, Erwin Schrödinger was one of the most fascinating personalities, the most fascinating intellectuals of the 20th century, and with very wide interests both in science and in other areas. In physics in particular, he both worked in experimental physics and in theoretical physics, well, of course more in the latter and mathematical physics, but he started out as an experimentalist. And so it's, well, if only for that reason, it's of course very fit that there are several talks which will pertain to recent experimental finds in quantum theory. He was, of course, also a philosopher, and so there are also philosophical talks, and this whole history is so interesting that there are historical talks, naturally. He was a linguist and he was a poet and an extremely remarkable personality. I wish I would have learned to know it, but that was not to be. We heard yesterday the beautiful lecture of Jürgen Wren, where he, in the first 10 minutes or so, more or less derived the Schrödinger equation without blackboard and chalk, and or rather pointed out some of the links to the past, to Albert Einstein, to Planck, and in particular Louis de Broglie. And it's in particular this last point is of course worth a detailed study, and I am quite excited that we have here Professor Darrigol who will talk about that. But let me point out maybe one thing which also pertains to the later lectures here, that these original ideas were based on a sort of Anschauung in the space that we are all used to, in three-dimensional space, and this I suppose, or that's my understanding or reading of Schrödinger, that he was originally thinking of standing waves in free space, really like, well, I mean, his first paper, quantization as an eigenvalue problem, it's clear that he is thinking of analogous phenomena to standing sound waves, let's say, in a cavity. But he realized very quickly that, in fact, his ideas were much more far-reaching. Because if you look at a helium atom, let's say, at the two electrons in a helium atom, it's clear that you cannot describe this system simply by waves in free space. It's essential that in this case it's a wave in six-dimensional space. So the original Anschauung has, of course, somehow diminished, and this, in fact, realizing this is the key or is the first glimpse into the wonders of quantum mechanics, because it's here that the concept of entanglement is hidden or is manifest, and we will hear more about this in several of the lectures, I suppose, in particular that of Anton. Okay, so this is now these general remarks. Then I have to announce one change in the program, that is in the afternoon. It's a change in title of the lecture of Monty Heiblum. The new title is Entangled Electrons in the Solid State, Quantum Interference and Controlled Dephasing. Moreover, I would like to draw your attention to the exhibition of the Library of Physics that was also yesterday in the main building of the university, which is now here on the floors of the Erwin Schrödinger Institute, and moreover that there are some posters in the back, in fact, on this long blackboard, which is, I think, the longest blackboard north of the Alps, at least. And you will have opportunity to come to the common room, of course, and wander around. In particular, in the afternoon, in the evening, there is a reception at in the common room. And during this reception, I would like to announce it right now. Professor Herbert Pietsman has kindly agreed to say a few words to share with us his reminiscences of Schrödinger. He was, in a way, one of his last students. That's to say, he attended lectures of Schrödinger, and I think it would be very interesting to read. Okay, now after these words, I will now I want to introduce our speaker. I'm very pleased that we have here Louis Darrigol. He is Director de Recherche at the CNRS, based at Paris Diderot, Paris 7. He studied physics and history of science, first at the École Normale Supérieure in Paris, and then in Sorbonne and in Paris 7, and he presented his habilitation thesis on the history of quantum field theory in 1982. He has published widely in many areas in the history of physics, not only quantum theory. One of his fields are also history of hydrodynamics and Maxwellian electrodynamics and the theory of relativity. Professor Darrigol has received prestigious prizes for his work. I mention here just the Prix Pictet, which is awarded from the Society of Physics and Natural History in Geneva, and the Prix Grammatikakis Neumann of the L'Académie des Sciences, which he received in 2004. So, Professor Darrigol, the floor is yours.
Thank you very much to the organizers to have invited me to this celebration. It's really a great pleasure and honor for me to be here today. I apologize not to be speaking about Schrödinger himself. I've done so a couple of days ago in Paris. But today I will be speaking on Louis de Broglie. I've been asked to do so by the organizers, and I presume because it is usually commonly accepted that there is a link between de Broglie's famous dissertation and Schrödinger's discovery of the Schrödinger equation. So today what I'm going to do is try to explain to give you some idea of how de Broglie arrived at this very surprising idea of matter waves, and but what were also the limits of this approach and why much was left to do for Schrödinger after all. Here you have on this title page, you have just a little part of a famous picture of the Solar Congress. It's one of 1927. It's one of the few pictures where you see de Broglie and Schrödinger together, and then of Schrödinger here and de Broglie here. We also have Langevin, who plays an important role in my story. You have Pauli behind, who seems to be looking down on de Broglie. But I must now first give you some elements of the biography of Louis de Broglie. Something very rather surprising and mysterious even is Louis de Broglie really is not, if you look at his early biography, is a very unlikely major contributor to quantum theory, since he was born from an aristocratic family in which research in science would be regarded as a commoner's business. And he was born in a country which brought very little to the early quantum theory, which that was nothing essential. France was pretty backwards in this field, in fact, in the early years of the century, 20th century. So now, anyway, I had to try to see why nevertheless he managed to do something great. His early studies were not in physics, they were in history, but he got bored rather quickly with this subject, as I hope you're not. And then he read Poincaré. That was for him, he was very enthusiastic about reading La Science et l'Hypothèse, and that supposedly determined his decision to do science and to do physics and mathematics. So he enrolled in the physics mathematics program at the Sorbonne. And an important influence, of course, at that time on him was his brother, Maurice, since his father died young, when he was young, at 1914, when Louis was young. And his brother, Maurice, his elder brother, was largely responsible for his education, but his brother happened to be already a physicist, and not a minor one. He was running his own laboratory of X-ray spectroscopy in his own private apartment, with perhaps 15th century beautiful furniture, but also very modern, up-to-date equipment, and doing very respected experiments. So respected that he was chosen to be one of the secretaries of the first Solvay Congress in 1911. His brother helped him in this task and had the opportunity to see the proceedings of the conference before they were published, was of course very enthusiastic about it and determined his passion for quantum theory already. So the studies at the Sorbonne in this period of 1910 and from between 1910 and 1913. And then comes the war. He works as a telegraphic operator under the Eiffel Tower, and at the end of the war, he joins his brother's laboratory as what we would now call a house theoretician. That means that he was doing theoretical calculations to interpret the spectra, X-ray spectra that were produced in this laboratory. Well, at that time, Louis de Broglie remained in this period, a fairly unknown physicist, was not regarded as a major physicist, certainly, and his work was received rather ambiguously. His theoretical calculations were regarded as very ill-founded by the Copenhagen authorities, especially because he was not using the correspondence principle properly, as no one was able to do apparently outside Copenhagen. And you're going to tell you a lot about it yesterday. And but nevertheless, this work produced formulas that enable one to determine the inner structure of atoms in the X-ray spectra. And this formula turned out to be quite helpful, since there was a basis for Edmund Stoner's speculation in England about a new determination of the number of electrons in the inner shells of atoms. And this paper by Stoner was the important paper that Pauli used when he introduced the exclusion principles. So you see that after all, this early work of Louis de Broglie was not without historical impact. But on average, he remained a fairly unknown physicist at that time, around that time. Now I'm going to give you a series of insights that de Broglie or Darrigol had in the period preceding his dissertation. And these insights are rather, disparate, diverse, and but they have been combined in some way by de Broglie at a later stage. And the first one is what is not very well documented, because it's only after reminiscence, which is found in a manuscript by Louis de Broglie in the archives of the Academy in Paris. And in this manuscript, de Broglie tells us that really his first important idea happened a little after the first Solvay Congress, 1911. And it was the idea of a relation between using in quantum theory an analogy between action in mechanics, the action in mechanics, and phase in wave theory. So he was very aware of the analogy between Fermat's and Montagu's principles. So I remind you of Fermat's principle of 1662 is the principle of least time for the time that light takes to travel from one point to another through a medium. It's the medium theory. And this can be reformulated as a principle of least phase immediately. On the other hand, you have the Montagu's principle, which historically actually is related to the first, since it was found by Montagu by reinterpreting Fermat's principle in the context of the Newtonian corpuscular theory of light. And this new principle of Montagu stipulates that the action should be a minimum or an extremum, and where you have this expression P dr for the element of action, where P is the momentum. So you see that in this analogy, very clearly, the action is a counterpart of the phase. Now, quantization can be expressed as requiring that some so-called action variables that have some same structure as action, and it's kind of integral, the same as this integral there. This action should be an integral multiple of Planck's constant. Well, from a classical point of view, this is a very strange thing. But if you now think that the action is something like a phase, then from a wave theory theoretical point of view, it is quite natural to assume in some circumstances that the phase should be a multiple of something 2π, and so that you have stationary waves, interference, or whatever. And so de Broglie already had this idea, apparently, that the mystery of the quantum rules had to be found in some wave aspect, in some phase, but he didn't develop the idea at that time any further. There is a similar idea of trying to explain the quantum rules of quantum theory by a wave process. It's found in Marcel Grégoire's notion here of the hereditary field, the champ héréditaire, of 1999. This might seem a bit exotic, but I have to mention it because it was cited by Louis de Broglie himself as an important source of his own inspiration. So, what is this idea? Well, Marcel Grégoire was a specialist of acoustics and waves, modalities, and he had the idea that if you compare, for instance, the hydrogen atom as some sort of acoustic source, you should expect that the wavelength of the emitted radiation should be of the same order of magnitude as the size of the emitter. But in the case of the hydrogen atom, this can only be true if the velocity of light within the atom is much smaller than in a vacuum. And in fact, it should even be smaller than the velocity of the electron on this trajectory in the hydrogen atom. If this is so, Broglie will tell us, there is some kind of sillage in the wake, which is the dark part in the figure, behind the electron, which is revolving here on this circle. And in order to retrieve the quantum conditions, what Marcel Grégoire taught you is that whenever the particle catches up with its wake in the medium, it should encounter the wake in the same phase. And then, if you have this condition, you get some quantum condition. Well, the details of this theory are not very important, but the idea, you'll see, was somewhat inspirational for Louis de Broglie. Now I come to something which is probably more important, in fact, as a context for Louis de Broglie, is the idea that his brother, the brother of Maurice de Broglie, developed about radiation during his experiments on the interaction between X-rays and matter. Well, the commonly accepted interpretation of X-rays at that time was that they should be electromagnetic waves of high frequency, especially after Lau's experiments of 1912, which they showed that could be diffracted. But it was also known since the beginning of the century, and this was especially emphasized by Johannes Stark, for instance, that these X-rays could have a corpuscular behavior in certain occasions. For instance, if you imagine that the X-rays are produced by the impact of electrons on a surface, on a metal surface, for instance, as is the case in a typical X-ray tube, and then if you use the emitted X-rays to ionize a substance which is far from the source, if you measure the energy of the electrons produced by ionization, you find out that the energy of these electrons is of the same order of magnitude as the energy that served to produce the X-rays. This can only happen if the energy travels in a single direction from the first target to the ionized substance. And this is very bizarre from a wave theoretical point of view, except of course you expect to travel the radiation to travel in multiple directions. So this was quite paradoxical, and the paradoxes of radiation were strongly emphasized by Louis de Broglie around 1920. And the reason is that he was working on the theory of the photoelectric effect, or sorry, on the verification of Einstein's theory of photoelectric effect in the context of X-rays. Well, as you probably know, Einstein's photoelectric relation had already been verified by several people, but especially by Millikan. And but this has not convinced any major physicists to accept Einstein's light quantum. The reason is that there were alternative theories you could exploit in the case of the ordinary photoelectric effect, where you use not X-rays as the incoming radiation, but UV light. The target is a metal, zinc, for instance, but a metal is something complicated. It involves many particles, etc. So you can imagine a complex mechanism that will mimic the Einstein photoelectric relation. But in the case of X-rays, you are in a more pure situation from a theoretical point of view, because at that time there already was a model that worked very well for the effect of X-rays on matter, and in fact its effect is an effect on individual atoms, and even more specifically on the inner shells of atoms. So you can tell very precisely what happened. And then if you verify the Einstein photoelectric relation in this case, it really has a strong impact on and makes you very effect on accepting the light quantum, and it had certainly for Maurice de Broglie. So I remind you what was the theory of Valter-Kossel, in fact, in the case of the Bohr atom, for X-ray spectra. So you have this shell model where you have a succession of shells, K, L, M, and you have an impinging X-ray radiation that ejects an electron from one of those shells. Here's the K shell in this figure. And afterwards, you can have electrons from the upper shell falling into the hole that has been produced in this manner. And that's the so-called fluorescence spectrum. And so you have in this picture an explanation both of the absorption and the fluorescence and the emission spectrum. Now, in order to verify the photoelectric relation, you just have to measure the kinetic energy of these ejected electrons. And in order to do so, Maurice de Broglie simply used a magnetic curving of a trajectory. Here you have a magnetic field perpendicular to the screen, and so the trajectories are curved in this way, and the impact on the electron is a photographic plate, and the impact of the electron on the photoelectric plate depends on its velocity, therefore on its energy. And incidentally, you have to use in this regime the relativistic formula, so these experiments were also for the energy, so there are also verification of Einstein's formulas for the energy. But what is important for Maurice de Broglie is that he obtained spectra in this way that were quite similar in aspect, visually, to the spectra you obtain. Here are the X-rays that travel straight, and then you can have the diffraction, you can have the spectra for the X-rays, and you find that you have, in fact, similar spectra for X-rays and for the emitted electrons. This similarity was very striking.
And in fact, he uses the word spectrum in both cases, because for now, today, to speak of the spectrum of electrons, it's obvious, but it was not at that time. So Louis de Broglie was so struck by the similarity that he drew some important conclusions from the essence of the subject here. And here's what he writes: an extremely detailed correspondence between the corpuscular spectrum and X-ray spectra, which is so striking when one sees the photographic plates, must strongly attract one's attention to the sort of unity which exists in the radiation. The latter sometimes takes a periodic aspect, undulations, some other times a kinetic aspect, emission. He went as far as to introduce a frequency for the electron itself, K over H, if K is the kinetic energy of the electron. And this kinetic energy being related to these frequencies, to the frequency of the corresponding X-ray radiation when the atom interacts with the X-rays, when the electron interacts with the So now there is another comment which is even stronger. In 1922, there is something kinetic in the vibratory radiation and something periodic in the projections of corpuscles. All of this suggests more and more every day that the same reality manifests itself, sometimes under its kinetic phase, sometimes under its undulatory phase. This is not quite duality in Louis de Broglie's later sense, but you see that it seems likely that was favorable ground for the type of articulation of Louis de Broglie, as sort of the insights of his brother. But this was not the precise starting point of Louis de Broglie's speculations of 1923. Basically, the main ideas of Louis de Broglie that were found later in his dissertation all appeared in a series of little articles sent to the Compte Rendu de l'Académie des Sciences in 1953. So the basic idea, as Jürgen reminded you yesterday too, is the starting point is to assume that like quanta carry a small mass. Why is that? Well, because de Broglie believes so much in the analogy between matter and light that in order to be fully analogous to material particles, like quanta should carry a mass. That's the idea. And in fact, if you look at the few people after Einstein who accepted the like quanta, they were usually very unknown physicists and minor physicists who were interested in Einstein's like quanta. But they all were more naive than Einstein, and they pushed the analogy between like quanta and matter further than Einstein had done himself. And this is the case of Louis de Broglie. He thinks there must be a mass, of course a very small one, but there must be a mass for the like quanta. And one reason is that it's only in his view, in this case, that you have a well-defined dynamics, relativistic dynamics for a particle with mass. Yeah. So that's one of his major arguments. And another one is that if you assume a mass, a finite mass for the electron, that means that you have a one-to-one correspondence between the velocity of the particle and the frequency, associated frequency through Einstein's relation E equal h cubed. Yeah. So if you have this one-to-one correspondence, that means that there are quite a few typical wave effects that you can reinterpret as corpuscular effects. For instance, the Doppler effect, which is a frequency shift, can be reinterpreted as some corpuscular kinematic effects of the velocity shift in this interpretation. Well, the problem, if you assume a finite mass, is that there are something rather bizarre happens if you assume a finite mass for the light quantum. According to relativity theory, of course, there must be a rest frame in which a light quantum is at rest. Then in this rest frame,
If you associate to Einstein relation frequency nu0 equal mc squared over h, this can only be interpreted as the frequency of some internal oscillations, some stationary oscillation in or around a light quantum. Now, if you look at this oscillation, this stationary oscillation, from the point of view of the laboratory, in which, of course, the light quantum has very fast velocity, so the velocity of light, then in this frame, or in this frame of reference, the apparent frequency, according to Einstein's law for the dilation of time, will be given by this formula, but the relativistic energy formula is this, and you see that E is different from H2 prime here. So the Einstein relation is not preserved. So de Broglie wanted to solve this paradox, and the way he does it is by noting that the intrinsic oscillation, while it travels at the velocity v of the light quantum, remains synchronized with a progressive plane wave of a frequency given through the Einstein formula here, this frequency, and the phase, and it's true if there is a phase velocity which is chosen in this manner, specific manner, c squared over v, the velocity of the light course. Of course, this velocity is larger than c. That's why the Broglie calls it fictitious waves, non-fictive. And they are both, in this picture, waves and corpuscles. This is essential for Louis de Broglie. And it speaks about atom nuclear. I don't know how to translate this. So the picture here graphically is, that I drew, is something like that. If you have a wave seen at two different successive times. Here it travels at the velocity large v, here, capital V. And the particle travels at a smaller velocity. And if it was at the top of, at the crest of the wave at the first time, and if it is at the hollow of the wave at the third time, the internal oscillation, which is represented by this rotating arrow here, red arrow, this internal oscillation must be in phase, permanently in phase with the wave. That means that when it is upwards in the crest, it should be downward in the hollow. So this is this condition of synchronization between the internal oscillation of the particle and the phase of the wave, the traveling wave, the fictitious wave, which implies this relation. There is a simpler formal way to look at this, which is the one you are familiar with. Of course, now all these considerations of Louis de Broglie are forgotten. But the formal way is simply to say that according to relativity theory, well, the relativistic coherent way of generalizing this relation is regarded as the fourth component of the four vector, and write P equal H bar K for four vectors relation. And then the spatial component of this relation gives you the famous relation lambda or H over P, which actually was not originally written explicitly by Louis de Broglie, it comes at a later stage. And so you have this relation. Now, of course, what is interesting is that Louis de Broglie, having given mass to light matter, dared to use these pictures for material particles, since now they are particularly reverted the analogy, if you wish. If light quanta are so similar to light particles, and light particles should be similar to light in some sense, and you should use the same dual picture with both waves and particles mutually synchronized. And the way I told you, you should use the same picture for matter as well. And so de Broglie is trying this and shows it has a lot of very interesting consequences for him. The first one is that this analogy I mentioned earlier between Maupertuis and Fermat's principle, it's no longer an analogy, it's a relation of proportionality. You multiply Fermat by part and you get Maupertuis. Now, even more interestingly, if you look at the cross trajectory of an electron in an atom, and you
Suppose that the wave, the associated wave, also travels in a circle, and if you require that the internal oscillation of the particle should always be synchronized with the wave, and of course the particle, since it travels slower than the wave, it will be caught up by the wave several times. And so the idea is, so this is the reverse of the picture of Marcel Brillouin. So the synchronization must be preserved every time the particle and the wave catch up with each other. This is a base-and-basic idea, but it boils down, in fact, to the requirement, even though it's not the way the Broglie originally expressed it, but it boils down to the requirement of stationary waves on circles for the hydrogen atom. So very simply, you can say that for circular orbits, the circumference of an orbit must be an integral multiple of the Broglie wavelength, and that implies the rule of quantization for the angular momentum effects. This is the elementary reasoning you usually find. I wanted to tell you also that there is another contribution of Louis de Broglie at that time, which concerns the statistics of this so-called wave-coupled atom, as he says. And this is actually an important part, especially from Schrödinger's point of view. This is the one which most please Schrödinger, and which is the source, in fact, of Schrödinger's first contribution to matter waves. But I'm not going to detail this aspect of Louis de Broglie, just to tell you that this is natural statistics which should be viewed to the theory of the quantum gases, the Boltzmann statistics apply to de Broglie's waves that should be stationary in a cavity and should carry a variable number of particles, associated particles. All of these results are put together in the dissertation, the thesis of 1924, Recherche sur la théorie des quanta, and which is in fact a very striking and daring synthesis of the various aspects of the light matter analogy we have encountered in this earlier history. And but what in fact gives a very strong formal unity to this whole dissertation is truly the relativity principle. It holds everything together in a very consistent manner. And the thesis was defended in November 1924 in front of a jury including Langevin, Perrin, Mauguin, and Cartan. And I give you a few of the reactions. Langevin said this work showed a remarkable coherence and mastery, and he emphasized the originality and depth of the ideas. Jean Perrin's comment was if you catch all the nuances of the French, it's a little more ambiguous, because when you say un travail très intelligent, well, it means very intelligent, but also it may be a bit speculative, you know. When Einstein was most enthusiastic, you know, he famously wrote a letter to Langevin, who had asked him for his opinion, so Langevin had sent a copy of the dissertation, and Einstein's reaction was, hat einen Zipfel des großen Schweigs gelüftet. He has lifted the corner of the great veil. Metaphor. So, the reason of Einstein's is not about accidental, well, it's accidental in some sense, because it happened to be working at that time on the quantum theory of degeneracy in the so-called Bose-Einstein gas, and he had just found out that the thermodynamic fluctuation of this gas include a mysterious term which could be interpreted as the interference of random de Broglie waves in a partial volume cavity. So here is the connection with de Broglie's dissertation, and of course also the relativistic aspect of dissertation must have pleased Einstein strongly, and that may explain too his very enthusiastic reaction. And of course, this brought to many people these remarks by Einstein, who were opened their eyes and showed them the interest of de Broglie's dissertation, and this was a case in particular of Schrödinger, as is well known. But I remain with de Broglie, and now the question I'm asking is, what exactly was the scope of de Broglie's analogy between matter and light? It could have been limited, in fact, to an analogy between rays optics and particle dynamics, not the full wave optics, but optics in the rays approximation, as was the case, for instance, for Hamilton in the early 19th century. And in fact, there is, if you look at the dissertation, it's mostly, almost entirely, seems to be limited to these aspects. And but there are a few exceptions, and, or apparent exceptions at least. I give you a few relevant citations I can find. The first one is found in one of the confounding articles. An electron flow crossing a sufficiently small aperture will exhibit diffraction phenomena. This is the direction along which we should perhaps look for an experimental confirmation of our ideas. Interestingly, the prediction was not repeated in the dissertation. Schrödinger shied off the prediction, Schrödinger said it wrong. And, but he was asked by Mogin what would be a good experimental verification of your ideas, and he answered, well, diffraction. So he said it at least during the defense of the physics. Now here's another citation. The new dynamics of the material point is to the old dynamics, including Einstein's, what undulatory optics is to geometrical optics. Upon reflection, it will be seen that the offered synthesis appeared to be the logical crowning of the compared developments of dynamics and optics since the 17th century. That seems to be really strongly suggesting going beyond, of course, this limitation to rays. And there is something of the same kind in a dissertation of 1924, a dissertation of the same kind. Our dynamics, including the Einstein form, still lies behind optics. It still is at the stage of geometrical optics, and meaning of what you should go beyond. Well, all of this suggests that de Broglie had in mind a wave mechanics that would be in ordinary mechanics what wave optics is to ray optics. If this is true, in this case, it shouldn't have been too difficult for de Broglie to discover the Klein-Bondon and the Schrödinger equations. Indeed, if you really look beyond the approximation of geometrical optics and you look at the proper wave equation, which is compatible with the de Broglie's dispersion relations, as we will say today, well, there's not kind of ways of doing that. And the one very simple way, which is actually the one you find probably Schrödinger's earliest way, which is not the one you find in the published papers, but as Erwin Schrödinger has shown, which is most likely the first derivation, and in substance it starts from the general form of the wave equation for monochromatic wave of pulsation omega. And for instance, acoustic waves, you expect an equation here of this form with this function c of the location r. And now if you look at for locally brainwave solutions of this for various wavelength, you will be able for those locally brainwaves to apply the de Broglie relation, k equal p over h bar. And if you inject the result into this generic equation, you get the Klein-Bondon equation using no approximation. And if you do the non-relativistic approximation, you get the Schrödinger equation. Simple enough. Then why didn't de Broglie do it? I think there are many reasons why he didn't do it. And that's where I'm coming now. First, despite the few citations I gave you earlier, it is clear that in the de Broglie dissertation, there's really here is the focus on the approximation of geometrical optics, and on retrieving accepted results of the quantum theory, and not on making major spectacular predictions. Basically, for instance, he wants to show that with this picture you can retrieve Planck's Clarity law, you can retrieve the Bose-Einstein quantum rules, and show in a supposedly much more fundamental way, but this is all about retrieving accepted results of the earlier quantum theory. Secondly, I think one should never forget that for de Broglie, the basic picture of radiation is a dual picture, involving both corpuscle and waves. It's not a pure matter-wave theory, as it will be for Schrödinger. And this is important in a sense because the emphasis on Louis de Broglie is more between the coupling between the corpuscles and the waves than about the evolution of the waves. So he's not so much worried about finding an equation for the waves. But the most important point, the third one here, is that de Broglie believed that the matter wave should actually be electromagnetic in nature. They were not essentially new waves for him. And the best evidence for this conviction of this is found in a little known paper of 1925, after the dissertation, where he describes his formula for the intrinsic oscillation of an electron in its rest frame, as given by the stationary superposition of the retarded and advanced solutions of the D'Alembertian equation. In short, he applies the D'Alembertian equation of electromagnetic waves to his matter wave, and he's not looking at all for new equation, you see. So, the conclusion is that the same heuristic principle, the analogy between matter and light, which on the one hand leads de Broglie to the matter waves, is the same principle that prevents him from seeking a specific equation for these waves. Why believe too much in the analogy? But for him, to be fully analogous to light, the matter waves should be electromagnetic in nature because light is electromagnetic. Now, in order to go further, one had to take a fresh look at this problem, to put the emphasis on the matter waves and to put emphasis on the fact that in de Broglie's theory, one has been so far limited to an approximation of geometrical optics, which is approximation of small wavelengths. This is exactly what Schrödinger writes to Louis de Broglie after the fact, after his major discovery, on 26 March 1926. And in this letter, I left it in French to give the flavor of Schrödinger's French, but I will translate it. For small or fine phenomena, one must, both in mechanics and in optics, replace the geometrical treatment by a wave treatment. One might as well say physical treatment, taking it into account that the wavelength is finite and not infinitely small, as is assumed in geometrical optics and also in the old mechanics. So this is, his explanation, basically reversing the approximation of geometrical optics in order to get to the true wave theory of matter with this proper equation. This is exactly what he's doing. So now I will, I'm basically at the end of my talk, and I just want to summarize what I've been trying to say today. First, that de Broglie, despite being in a way unfavorable circumstances to make a major contribution to quantum theory, the circumstances were not so unfavorable in the sense that he was rather privileged, I think, to be in such an excellent laboratory as Maurice de Broglie, to have good contact. I forgot to say that he was attending Langevin's lectures. François Langevin was an important figure and the best source of information, understanding, also Léon Brioin, I should mention perhaps, for quantum theory and relativity at that time. So, in fact, de Broglie was privileged in the sense to be in contact with these people. And and then I have shown you that he was exposed, or he had various ideas that seems to be pretty disparate, but managed to combine them in a very consistent manner in his dissertation. And as daring, as crazy as the idea may have seemed originally, it ended up, and perhaps the consequence of this inner coherence, to be a true idea in some sense. And but now the shortcomings of this whole strategy is that the very heuristic principles, as I told you, that was so useful to de Broglie, well, there were two major heuristic principles, the relativity principle, of course, and the analogy between matter and light. But the latter principle was both a guide, and it was really this perhaps naive idea of ascribing the finite mass to the light quantum, but from a heuristic point of view is quite essential for Louis de Broglie, because that triggers the whole train of thought. But at the same time, it was retrospectively, you know, the backside of this analogy is that it prevents de Broglie from looking for a new wave equation, which is left to Schrödinger and all the Dutch developments. Just now to conclude the conclusion, picture of Louis de Broglie, somewhat later picture, as you can tell, showing the equation in which he had discovered and the relation he did discover here in a non-relativistic approximation. Thank you very much.